Okay, so let's see what happens for SO3, and that will actually make things clearer. So we now show that only those group elements, in physics we call them transformations, continuously connected to the identity are part of SO3. Okay, we're going to show that now. So let's start with O3. And it should have how many generators? 3 generators, right? Because it's a 3-dimensional group. Okay. So the parameters are some 3-dimensional vector with theta 1, theta 2, and theta 3. All right. So now, let us look at an infinitesimal element, or an element, look at an, okay, sorry. Okay, we look at an element that is infinitesimally close to the identity. So we can write that element as, I know we've been using O for the, okay, let's just keep using G here. So G, delta theta has the form of the identity plus delta theta dot x, right? That's how we have defined the generator. Now, let's define theta to be related to delta theta in the following way. Theta is defined to be theta over n is equal to delta theta, okay? So n is going to be some integer. We have not specified n yet. Okay, n is going to count the number of times we are going to apply this element. And because it's, yeah, okay, we are going to apply this element. So now let us apply G delta of theta n times, then the element that we get is 1 plus delta of theta to the power n, and that we can write that as 1 plus, oh sorry, I forgot the generators here. So it's delta theta a vector dot x, and this is 1 plus theta by n dotted with x. Okay, we have done really, and this is applied n times. All right. So what are we doing? We are basically starting at the identity, and we are, going in the x direction n times. So each of these, displacements in the group manifold is parameterized by delta theta. Okay, so the number of times we are applying this, this plus this is n. All right. So now let us take n to infinity, while keeping theta finite. Okay, not infinitesimal, finite, right? So then we get an element which we call g of theta, and this is the limit of the n integer going to infinity, and it's 1 plus theta divided by n dot x to the power n. So can someone tell me what this is?
Exponentiated to theta.
So this is the definition of the exponential. All right. So what have we learned? We have learned that any element of O3 that can be continuously built up that is continuous, can be continuously okay, let me just rephrase it. That is continuously connected to the identity can be written as in this form, e to the power theta dot x. Okay, are you convinced? I mean, it's not a proof, but I think it's pretty convincing, yeah. All right, so now let's take the determinant of this element. So we write this as g theta. So the determinant of g theta, what is it? To evaluate this, we use a formula which you should have learned in your algebra or linear algebra course, which is if I have a matrix and I take its determinant, then that's going to be equal to the first taking the log of that matrix and then taking its trace. Okay? Do you guys know this?
No, actually I don't, and I have taken a linear algebra course.
Okay, so maybe we will derive this in the upcoming tutorial, okay? But this is an extremely, extremely useful formula. Like you have to know this. If you're going to do physics, you have to know this formula, okay? And often I forget this. So I have to either look it up or kind of guess it. Or, all right, so this is extremely useful. So if I now use the fact that we can write g of theta as e to the power theta dot x, and then I take the determinant of g of theta, then I will have e to the power trace of theta x, right? Which, I mean, trace is a linear object, so I can actually write it as theta dotted with a trace of x vector, okay? But if I look at this equation, the right-hand side of the equation, right-hand side has the form of e to the power some real number. Now, we know that this has to be either 0 or positive, right? And therefore, the determinant of g of theta must be real or positive. So this includes SO3, but excludes determinants of, say, g -1, right? So therefore, we have shown that those elements of O3 which are continuously connected to identity have determinant 1. All right, any questions?
Could you please go up a little bit?
Sure.
Yeah, so this equation, determinant of m equals trace of log of m. I don't think this is correct. I think the correct one should be log of determinant of m equals trace of log of m.
Oh, yeah. Okay. Sorry, yeah. You're saying, sorry, what is the correct thing you're saying?
Log of determinant of m equals to
Yeah.
trace of log m.
Log, yeah, I think, yeah. Yeah, you're right. Log of m, log of determinant of m. Okay, let's see. Determinant of m is trace of log of m. Yes, you're right. Yeah. Sorry. Thank you very much. Yeah. Thank you. Yeah, this is not correct. As I said, I forget it myself, and then I have to look it up. And I know how to use it, but I don't remember it. Remember the all right.
Sir, I had a confusion. Could you say how the theta was like brought up outside the trace?
Right. So the theta, because it's a trace is just a linear thing, right? I mean, yeah, that's good. So if I look at theta dot x, it's essentially theta I xi, right? So these are numbers, but these are matrices, right? So when I say trace of theta dot x, what I mean is, trace of the matrix, but the matrix is just this thing, right? So this is theta I, the matrix xi. We are summing over, say, the AA component, right? That's what trace is, right? So this is theta I trace of xi, right? And therefore we can, if we think of this as a set, this is basically what I've written as theta dot. Yeah, I should really write this as theta I xi, not theta dot trace of xi, trace of x. Maybe that would make it clearer. Right, so if I go back, and maybe what I should have done is write this as theta I, and this is trace of xi. Okay, now here, and the dot should not be there because I'm.
Yeah.
Okay, yeah, thank you very much. All right, any other questions or comments or corrections? All right, so this shows that the connected part of O3 is the one who has determinant +1, right? So now